Section 1.4 is about changes, and there are two basic types of changes we're going to look at: physical change and chemical change. What we have here is an example of a real-world object. We have water boiling away inside of a teapot, our coffee pot here, and in this case what we have is water molecules that are changing from a liquid state to a gaseous state. And this is one example of a physical change. On the right hand side we see what the molecules are doing. They're undergoing a change from where the water molecules are associated closely with each other and sliding around each other but not free of each other, going to the gas state instead, where one molecule is free from interacting with the other and they're flying around pretty much wherever they want to go. That is a physical change from one physical state of matter to another. Here's another physical change, one going from a solid to a gas. And again, what we're looking at here is a alteration of the chemical state of matter, the state of matter for that particular compound. So when we have carbon dioxide solid, this is what we actually have in dry ice. We have that rigid structure, crystalline type structure, and when this sublimes, turns directly into a gas without becoming a liquid in between, we have carbon dioxide gas molecules that are completely free from each other. Now in a chemical change, you can see as an example here with a nail rusting, which is basically the chemical change that you always see in any chemistry textbook. We go from iron atoms in the original iron nail, where it is nicely evenly distributed, to iron oxide, which is iron and oxygen nicely distributed in a solid form. But now this is a different chemical composition. In fact, iron oxide is a different chemical compound with its own properties. Nails are shiny and silver and metallic. Rust is kind of brown and flaky and more crystalline and falls off into a nice powder if you brush against it. So these are different chemical substances, just like carbon monoxide is different from carbon dioxide and water is different from hydrogen peroxide. Iron and iron oxide are different chemical compounds. So what's the difference between, how can I kind of distinguish between the two of them if I'm just looking at it? Well, a physical change is usually indicated if I can just change the temperature of the sample and recover the original substance that I had. So if I have ice and I heat it up and it melts and it becomes liquid and it looks like water, but then I put it back in the freezer again and it turns back into a solid that looks like ice, that's a physical change. There's no difference in what the chemical composition of those molecules are. So instead, all we did is just change from one state of matter to another. Chopping up something into pieces and then putting them back together is the same thing. If we're just rearranging things in space, that's just a physical change to a substance and not a chemical one. So what's the molecular difference here? And I didn't expect these molecules to be circling, but hey, bonus. So a physical change, which we see on the left here, is a change of state or a change in arrangement of existing chemical substances. So water molecules might change from a liquid to a gas, or a gas back to a liquid again, but they are still water molecules. There are still one oxygen connected to two hydrogens. No bonds between atoms have been disrupted and changed or broken or rearranged to form different groupings. It's the exact same molecule, just in different states of matter. Now, on the right, we have a chemical change. Now here we have hydrogen peroxide turning into water and oxygen. And when this happens, what we're actually seeing is there are molecules that are connected in a certain way with two oxygens together with hydrogens on the edge, turning into different chemical compounds. So bonds between atoms have to break, they have to reattach to each other in some way, and you end up with a completely different set of chemical compounds with their own chemical properties.
Physical change, no bonds have been rearranged, no atoms have new partners and new configurations. With chemical change, though, the atoms are rearranged and bonded in different groupings when the process is done. Now, chemical change is not so easily undone. Usually just changing the temperature, cooling it back down, is not going to give you the original substances. An example of this is if you bake a cake, you know it's a chemical change because you can't just cool the cake back down and get sugar and flour and eggs and all that sort of thing back. It's not going to recover itself and be separatable just by normal physical type means. Heating, cooling, are trying to physically separate. Okay, so how about this one? Salts are sugars dissolving in water. So here's our molecular diagram on the right. We have a bunch of sugar molecules and a bunch of water molecules. We know what the two things look like. We mix them together. Here's our original sugar molecules, unchanged. Here's some water molecules, unchanged. So this is which? This is a physical difference. So even though it looks like something has changed property-wise, a solid looks like it's disappeared and maybe turned into a liquid, it's not turning into a liquid. It's actually just being so finely mixed together that you can't see the individual crystals of sugar anymore because they're so evenly mixed they basically become invisible to the naked eye. And so this is a physical change. When things dissolve, we're only looking at a physical change. Alright, what about propane gas burning? Here we have some propane molecules, which are these collection of carbons and hydrogens, 3 carbons to 8 hydrogens. And you combine this with oxygen, it's O2, that's you don't see here, but that would be 2 little spheres bound to each other. In a molecular description, they turn into carbon dioxide and water vapor. So this has different connections than the original set of substances. So therefore, we know that this must be a chemical chain with different arrangements and connections of atoms in the products. And so, what do you think? Eggs cooking. Think about it. It's gas. That's chemical. We know because we can't easily undo that just by separating the pieces from each other or by just cooling or heating this up to try and recover the original. That doesn't work. Once you fry an egg, it's fried, it's not going back to a raw egg again. How about water burning, turning into gas? That's a physical change, because all you have to do is cool it back down, and it's still water, whether it's a gas water, vapor, or liquid water. And how about this guy? This molecule, whatever this happens to be, looks like acetone. In the second picture, it's just a little bit wider apart, but we haven't changed any of the attachments, so it's just a physical change. And how about this one? Some methane molecules and some oxygen molecules, so it's turning into carbon dioxide and water. Okay, so we've changed what molecules are. It's a chemical change. Okay, so we have water over here, more spaced out, widely distributed water on the right. Which one is that? No change in the attachments or the ratios, so that's a physical